I will talk a little bit about resources for Mirage. I'll give kind of a top level overview about how it works, and then show a typical workflow for how you would create some simulations, and then step a little bit in more detail through an imaging simulation, which is also what the following notebook will cover. And then finally, there's some notes for installation and setup. And so just before we leave this page, I'll point out that these three images here were all created with Mirage. These are three of the different modes that it can do, which is you have just a random star field. Here you've got galaxies, which are 2D Sursic profiles. And then this is a wide field slitless simulation where all the sources have been dispersed. So just quickly, Mirage is on GitHub, so here's a link to the repository. Documentation is online at Read the Docs, and you can install it via PyPy. And if you have any problems or questions after today, you can always send a question to the JWST help desk, or you can submit an issue directly on the GitHub repository. So at a top level, what does Mirage do? It creates high fidelity simulations. It covers NIRCam, MIRIS, and FGS in most of their modes. And the outputs are level 1B files, so equivalent to what you will get from in-flight data, equivalent to the uncal files that can go through the pipeline. So Mirage can cover NIRCam, MIRIS, and FGS imaging modes. It can do wide field slitless spectroscopy for NIRCam and MIRIS. It can do imaging and GRISM time series observations for NIRCam. And then for MIRIS, it can also do the AMI mode and also the SOFS mode. And also, you can add sidereal and non-sidereal sources, so you can have moving sources going through the field of view. So at a top level, I like to think of Mirage as kind of a three-step process. The first is where it will create what we call a seed image. And this seed image is just a 2D noiseless count rate image. So the only signal in the seed image is from the astronomical sources. And the sources are input, the user inputs source catalogs, so that's how you control what appears in this seed image. Once you have the seed image, the Mirage will move on to the second step, where it will take a dark current exposure, and this will be a dark current exposure from ground testing. So it contains all of the real noise sources in NIRCam or MIRIS FGS. So 1/f noise and read noise and bad pixels. So it'll take that exposure and it'll kind of rearrange it into the readout pattern and the subarray size that you request. And then the third step, Mirage will take the seed image, translate that from the count rate image into an exposure with multiple groups, and add that to the dark current exposure. And then in that process, it will also add Poisson noise and cosmic rays and other detector effects in order to make the final output as realistic as possible. In terms of inputs, we'll see all this in the notebook, so I'm going to kind of go a little bit quickly over it here. But sort of similar to what MIRISim has, Mirage uses an input YAML file, which contains a bunch of different parameters that describes how to create the simulated data. And so Mirage will take one of these YAML files per exposure per detector. And we'll look at an example later, but you can specify, which instrument, subarrays, filters, reference files, and all that kind of stuff. And since these input YAML files are quite large, the easiest way to make them is to start from an APT file. And we'll see how to do that in the notebook that follows. The final output, as I mentioned, is a raw file. So units are DN. It's equivalent to the pipeline level 1B files, the uncal.fits files. There's also an option to output a linearized ramp. So in this case, it's equivalent to sending this raw file through about half of the detector 1 pipeline. So the signals are all linear up the ramp, and reference pixels have been removed and all that, but no line fitting or anything has gone on. And those are just a little bit easier to look at, but generally I create the raw images and then run them through the entire pipeline. And then there are some intermediate outputs that can be useful. So the seed images are great as a sanity check to make sure sources are where you think they should be, and that they are the brightness that you think they should be. And it will output a catalog of the cosmic rays that are added and a catalog of the sources that are actually on the detector. And then for modes where things are dispersed, like wide field slitless or GRISM TSO, you'll also get a seed image of the dispersed signal in addition to the imaging part of it. So typically when I create a simulation, the first step is to gather all of your inputs. And so the first part of that generally is to create source catalogs. And so we'll spend some time on this in the notebook, but Mirage has some convenience functions to generate source catalogs, or you can do it manually. There are several different types of notebooks that you can use depending on what mode you're simulating. The next input you don't need, but makes things much easier, is the APT file. So if you can export the XML and pointing files from APT, and we'll see how to do that. And then there are a few other observation type pieces of information that are necessary as inputs, like what background level you want and what roll angle you want to use. So once you have all those lined up, you feed them into this YAML generator function, which will then create the YAML files for every detector and every exposure in your APT file, in your proposal. And then once you have those YAML files, you can call, depending on what mode you're simulating, you can call the appropriate wrapper script to actually create the data. And then the outputs from those can go right into the JWST calibration pipeline. So just to step kind of quickly through those steps in a little more detail. As I mentioned, the source catalogs, they're just ASCII files. There are a bunch of different types, but in this case, we're going to simulate just a regular imaging data. So we'll focus on 3 types of catalogs, one for point sources, one for galaxies, and one for extended sources. And in this case with Mirage, extended is it's a catch-all, where if you have some object that's more complex than a point source or a 2D source profile, if you have a little FITS stamp image of that source, you can feed it in using this extended source catalog, and Mirage will read that in and place the source where you ask it to. So the next step, as I mentioned, is if you have the APT file, if you export the XML file and pointing file, those are the 2 files that Mirage will read in. There is in the Mirage repository well, I should say in the documentation, there's more details on this. And there are also example notebooks in the repository on GitHub showing how to do all this. Then you place your catalogs in the required input dictionary, which we'll see how to do later. And you add these optional inputs, and then you run the YAML generator. And then, as I mentioned, once you have these YAML files, you run the simulator itself. In terms of outputs, there's the seed image that I talked about. Everything is saved in a log file so that you can make sure that Mirage did everything you expected it to do. And if it crashed, it will save the trace back. There will be a table of the cosmic rays that Mirage added, so it will give you the location on the detector as well as the frame number, so you know where that is. It will output these source catalogs that contain only the sources on the detector. So if you feed it, if your input catalog is some massive catalog that covers a huge swath of sky, this is kind of a convenient way to see exactly what's on your detector. And then the actual raw or linearized output data, science data. And then at that point, you're ready to run the pipeline and you run your post-pipeline analysis. So I just have a couple links here to pipeline documentation, post-pipeline notebooks.